This is Jack Jackson. We're going to go over part 2 of our introduction to the derivative in this video. So let's go back and just review real quickly. We first started talking about this introductory example where we looked at position, time, and velocity. And we had this car going down at interstate at different times and positions, and we wanted to estimate the speed. And for example, one estimate was to take basically the slope formula and say take a point of interest, say right here at this point, and then take a nearby point, say this one right next to it here, and do a slope. And we also did it maybe with that point and one other, but use this and any other one point as an estimate of what's happening exactly at time t equals 2 in terms of velocity. So what we want to do is we want to take that basic idea now and to apply that now to a general function, not necessarily in this particular context. So let's switch to a general function, and we're going to use the same basic technique we did to find the estimate we just talked about, estimates 1 through 3, but do this for a general function. So now we're going to let f be a function of x, and we're interested in the average rate of change between 2 points in the table or on the graph, with one of them being a point of interest where x equals a for some fixed number a, and the other one is going to be a nearby point to that point. And the nearby point, we could call it tf of t, but of course t is just a plus some change in x, a plus delta x. And of course then the y would be f of that a plus delta x. Or since delta x is a little bit harder to write, we could replace delta x by the letter h. So we could write it as a plus h and f of a plus h. So now what we're looking at is our 2 points in the table. One is a f of a, that's our point of interest, and a nearby point which we might represent the x in one of these 3 ways and the y. X is one of these ways and its corresponding y like this. So what we're looking at is what's called the difference quotient, is just the ratio of those differences, that is a fraction, delta y over delta x. And of course that's just the slope, so I use the letter m here for slope. Okay, so if we look in our table here, we're just subtracting the y. So if I use the last version here, which should have an a there, f of a plus h minus f of a over, well, a plus h minus a is just h. So delta x and h are the same thing. Or if we replace h by delta x, which is what it really is, then it's written this way right here. Or if we let a plus delta x be t, then this is just f of t minus f of a over t minus a. So those are all different ways of saying the difference quotient. I normally think of the one in the box as being the main way we would write a difference quotient, but actually all of these are really the same thing. It's nothing more than just the slope formula. But specifically, we're thinking of the point a, f of a, as being a point of interest, and we're going to a nearby point for some small delta x, that is some small h, and finding the point there, then finding the slope. So notice that the difference quotient then is the average rate of change between 2 points in the table or on the graph, where one is the point of interest, the other is a nearby point, and notice that's going to be a slope of a secant line between 2 points on the curve, where one is the point of interest and the other is a nearby point. We'll look at this graphically, visually here in just a few minutes. Now, why is it called a difference quotient? Why those words? Well, difference means subtract, quotient means divide, and so what we have is a division problem, answer to a division problem, quotient, of 2 differences. Notice both the top and the bottom are differences. Difference of y in the top, difference in x in the bottom. So it's a quotient of 2 differences, hence the name difference quotient. So let's illustrate this now with a specific example where we're given a formula. So let's see if I can get you to answer these questions as we go. So if we let f of x be given by this formula, 1/20th x times x minus 6 times x plus 4, let a be 4 and h is 1.5, what is the point of interest we're talking about? Okay, press pause, work this out, and then come back. Okay, the point of interest is when you let x be a. And of course, if you let x be a, you plug in a, which is 4 in this case, and you plug it in here. Let's see what we get here. 4 plus 4 is 8. 4 minus 6 is negative 2. That's negative 16. We get a 4 here. Multiply those out, divide by 20. That turns out to be exactly negative 3.2. And we'll see this on the graph in a few minutes, and on the graph it's going to be the blue point. Okay, in a minute. So what's the nearby point we're interested in? See if you can figure that out and then come back when you're ready. Pause. Okay, well, the nearby point is a plus h for the x. So 4 plus 1.5 is 5.5 for the x, right? And then we plug in 5.5 in this formula, 5.5 in place of x here, here, and here, and I just worked it out on a calculator, but we get that amount there. In fact, let me just work that out on a calculator. Okay, it's just so you can see that. 1 over 20 times x is 5.5, times 5.5 minus 6, times 5.5 plus 4, and we get, there's the value that we got. So I can actually put that, we'll put that right in there. And there is the calculation there. Okay? What's the difference quotient? Well, the difference quotient is the slope between these 2 points. So it's that second y, negative 1.30625, the y of the nearby point, the x, yeah, that's the y. The y of the nearby point minus the y of the point we're interested in, negative 3.2. And then the difference in the two x's here. Of course, the difference of two x's is just going to be h, 1.5. And you work out this arithmetic in the top. And we'll see, so that's negative 1.30625 minus a negative 3.2 is the 1.8, etc. Divide by 1.5, and that works out exactly nicely to be 1.2625. Now, illustrate these graphically. How can we do that? Well, we start by graphing the graph. Now, this graphic here is from a GeoGebra sketch that I made, and this sketch works dynamically. You can change the value of a in the sketch, not here, but in the sketch by sliding this slider here for the a, change h here, and you can change some things here, but it's set up where we want it to be right at the moment. So notice I have the same formula here. So the purple graph is the graph of the function. The blue point's our point of interest, 4, negative 3.2, a, f of a. The nearby point's the green point, a plus h, f of a plus h. So we move over to the right a certain distance, h, which is 1.5. And of course you see this is 5.5 for the x there. And on the table over here you see it rounded off at negative 1.31. It was actually negative 1.30625. So now we can see the vertical change here is this little distance here. Horizontal change is here. From left to right here, they're both positive. So divide those two, and we get the slope that we just came up with, 1.625. Okay, and that is the difference quotient. Okay, 1.2625, and here it's rounded off as 1.26. Okay, so you can see that as the slope between the blue point and the green point on the graph, which is the slope of that line segment or that line that's going through here. And so that green line is what we call a secant line because it touches the graph in two places. So if we zoom in a little bit more closely here, you'll see the interesting points, and I'll use sort of the generic labels here. You've got your purple graph here. You've got your a comma f of a, which is the blue point. you've got a nearby green point, which is a plus h comma f of a plus h, and we want to find the slope of this green secant line. Vertical change, that's the difference in f of a plus h minus f of a. That's this length here. And then h is this red length here, which is just a plus h minus a. So this is delta x is the red one. Delta y is this vertical green thing. And then the slope of this slanted green line is the difference quotient. Okay? Now we'll pick up in the next video talking about the symmetric difference quotient.